9. We have a go for the main engine start. 5, 4, 3, 2, 1, 0. Booster ignition and liftoff of Columbia. A new decade of spaceflight begins.
From the tower.
Slow, that's the case. Yeah, you're
Reindeer touchdown.
We have a go for main engine start. 6, 5, 4, 3, 2, 1. Ignition and liftoff of Discovery and the Ulysses spacecraft bound for the polar regions of the sun.
That space shuttle orbiter is rocketing into space. But what is space? How do we get there? How do we stay there? And how do we get back to Earth again? Well, before we answer these questions, let's look at some history of manned rockets. This man, Robert H. Goddard, is considered to be the father of modern rocketry. He began testing rockets as a young man. And in 1926, he launched the world's first liquid propellant rocket. He was also the first to propose using both solid and liquid propellants on the same rocket. Why is that an important idea? Because that's how we boost the space shuttle into orbit today. It was in 1956 when a team of scientists and engineers, led by Wernher von Braun, launched the Jupiter C rocket. This was the first time that we launched anything that went high enough to get into space. 2 years later, another Jupiter C traveled into space. But this time, it left a satellite up there to orbit the Earth. Then, in 1961, only months after the Soviet Union sent their first astronaut into space, NASA launched the first American into space on board the Freedom 7. Things were moving pretty fast. First, we had the Mercury program, then Gemini, and then, just 8 years after the first human went into space, a Saturn V rocket launched the Apollo spacecraft that carried the first astronauts to the moon.
That's one small step.
Today, astronauts fly into space in a different vehicle. The Space Shuttle Orbiter. To give us enough energy to get into orbit, we use special engines and propellants. Let's look at the shuttle a little different way. This is what we call the stack, sitting on a launch pad here in Florida. Let's look at it the way an engineer might look at it. The solid rocket boosters, or SRBs, burn a solid fuel. The external tank, or ET, carries liquid oxygen and liquid hydrogen for the shuttle's main engines. This combination of solid and liquid propellants are very powerful. For launch, we start the liquid main engines first.
3, 2, 1, and we have solid.
Then the solid rocket boosters ignite and lift the whole stack off the pad.
On a course mission, and we observe the tower.
Downrange 22 nautical miles.
The solid rocket boosters push the shuttle for about 2 minutes up through the thickest part of the atmosphere. Then we separate from the boosters.
SRB-7 was that something.
The shuttle's main engines continue to burn for another 7 minutes, pushing the orbiter fast enough to get into space.
Houston Discovery.
Go ahead, Tom.
Command source is MDM.
Okay, and can you give us a deploy time, please?
And here's the result. We're in space. But where in space are we? In other words, how far above the Earth have we come? Well, let's use this picture to help explain. Here is the surface of the Earth. Here would be the Earth's highest mountain, Mount Everest, which is about 6 miles high. And right here would be where commercial airplanes fly, about 6 to 7 miles above sea level. The astronauts that went to the moon went 240,000 miles above the Earth. And if we could put that on this picture to scale, it would be 5,000 feet this way. Well, where does that leave us here in the space shuttle? Well, right now in the space shuttle, we are about right here, 160 miles above the Earth. For example, though, the space shuttle can even go higher. STS-31 that deployed the Hubble Space Telescope went all the way out to here, 300 miles above the Earth. So what's it like up here? Well, let's do a weather report from space.
Well, Tom, I'm going to have a little problem with that because there is no weather in space. In order to have weather, you have to have an atmosphere. Up here in the space shuttle, we're well above the Earth's atmosphere. So I can't give you a report on the weather, but I can tell you what the conditions are going to be like outside today. We can expect a scorching high of about 300 degrees Fahrenheit outside today in the sun. That's about 150 degrees Celsius. Down to a real freezing low of 150 degrees below zero, which is a minus 100 degrees Celsius in the shade. We can expect the relative humidity to be zero, and our barometric pressure is also going to be zero. Now, some of our viewers out there may be wondering, why are these extreme conditions outside when we're only 160 miles up above the Earth's surface, and the living conditions down there are so nice? Well, the reason is down on the surface of the Earth, we have an atmosphere. The atmosphere performs as a protective blanket for us when we live down on the surface of the Earth. Here, for example, is a picture of what the Earth looks like from a satellite 23,000 miles above the Earth. You can see that much of the surface of the Earth is covered by clouds. These clouds are the part of the atmosphere that you can see, the visible part of the atmosphere. The clouds are made up of water molecules. Those water molecules are what account for the relative humidity of our atmosphere. The total weight of the atmosphere above a point on the surface of the Earth is what it makes up for the barometric pressure. Now, we don't have to worry about our climate here in the space shuttle when we're up here in space because we have an air conditioner, what we call our environmental control system on board. This environmental control system will maintain our temperature a nice, comfortable 77 degrees Fahrenheit, which is about 25 degrees Celsius. Relative humidity will stay at about a constant 50%, and our barometric pressure will be about 29.92 inches of mercury. Back to you, Tom.
Thanks, Bruce. As you can see, the environment in space is very harsh. So here in the orbiter, we have to make the environment duplicate the environment that is down on the Earth's surface. And even though we're over 150 miles up in space here, the pressure inside the space shuttle is almost the same as it is at sea level. See, it's fooled this altimeter into reading almost zero.
Well, now we know where space is and what space is. How do we stay here once we've arrived? Well, 300 years ago, an English scientist, Sir Isaac Newton, figured out a way to do this. He began by showing a very high mountain. The imaginary mountain was so high that its peak poked above all the atmosphere. He put a cannon on top of the mountain and fired cannonballs. We'll use baseballs. Okay, here's our imaginary mountain. Let's pretend that we can climb to the top of this mountain with a sack of baseballs.
Now if we throw one of these baseballs straight out from the top of the mountain, would it go straight out like A, fall straight down like B, or fall in a curved path? While C is correct, the baseball would fall on a curved path. Even on this tall mountain, it still feels gravity. This is because the ball has two motions acting on it at the same time. It's trying to go straight out, and it's also falling toward the earth. The result is the baseball travels on a curved path and lands right here. Now let's throw another ball, only this time much faster. See, it goes farther than the first. If we throw another ball even faster than the last one, it goes farther still. So the faster we throw the balls, the farther around the earth they go. Now we'll take our last ball and throw it as hard as we can. Just like the other balls, it falls in a curved path. But this one is moving so fast that it circles the earth. We'll have to duck to miss it. But it won't be safe to stand up for a while, because unless something gets in the way, the ball will continue to fall around the earth on a curved path. We call this an orbit. Of course, the space shuttle doesn't launch from a mountain, but we still need a lot of speed to get into an orbit around the earth.
So, how fast do we need to be going to get into orbit? Well, if the space shuttle had a speedometer like the one in your car,
it would have to get all the way to 17,500 miles per hour to make it into space.
So how fast is that? Well, it took the early pioneers months to cross the United States by wagon. It took the first transcontinental trains a week to cross by rail. It would take about 3 days of driving round the clock to get across by car. And it takes about 5 hours for the average airliner to fly coast to coast. But on board the shuttle, we cross the country in 10 minutes. That's about 5 miles a second. You see, the space shuttle goes around the Earth 16 times every Earth day. That means we see a sunrise and a sunset once every 90 minutes. This could be a problem. Up here on the orbiter, if I woke up when it was light, and went to bed when it was dark, I'd be getting up and going to sleep every 45 minutes. That wouldn't work. So instead, we just plan out our days like we would on Earth.
Another thing you should know is we just don't float around on the orbiter because there is no gravity. We still feel Earth's gravity. So why are we floating? Because we're falling. Let's say the string is gravity. And let's say this apple is like a spaceship orbiting the Earth. You see, it's gravity and our speed that keeps us in orbit. Without gravity, we would fly off into space and never come back.
Here's another example. When I drop this apple on Earth, it falls. When I drop an apple here on the space shuttle, it falls too. It just doesn't look like it's falling. And that's because we're all falling together. The apple, me, and the orbiter. But we're not falling towards the Earth, we're falling around it. Let's imagine that we can send Bruce down to the nearest elevator on Earth. The elevator is going to the top of a very tall building. Suddenly, when he reaches the top, the cable breaks, and the elevator car with Bruce in it begins to fall. What will happen inside the elevator? Well, since he's falling and the elevator is falling at the same rate, he starts to float. His body isn't pushing on the inside of the elevator anymore. He has no weight. He's weightless. If he had an apple with him, it would float too, just like the one in the orbiter, because Bruce, the apple, and the elevator would all be falling together. It'd be a fun ride until he hit the bottom. And that's why things float around up here, even really big things, because we're all falling on a curved path around the Earth.
Well, now our work in space is done, and it's time to go home. So how do we do it? Well, first, we have to slow down. Let's go back to our imaginary mountain. Here's our baseball orbiting the Earth. It's going around every 90 minutes, too. We know the other baseballs weren't able to get into orbit because we didn't throw them fast enough. Now, to bring the baseball back from orbit, all we have to do is slow it down just a bit. Watch what this looks like. Those were our maneuvering engines firing. We use them to slow down. Here's what it looks like from outside the orbiter when they fire. They slow us down just enough to make a safe descent. Just like the baseball, we've got to slow down to get out of orbit. We glide back to Earth under computer control until our altitude is about 50,000 feet. Then the commander and pilot take over and land our space shuttle just like an airplane.
Space is great, but a safe touchdown sure feels good. After traveling 2 million miles in 5 days, it's nice to be back home again.
So now we know that it takes a lot of power to push the orbiter through the atmosphere and into low Earth orbit in space. We have to go very fast to stay in space, and we have to slow down just enough to allow Earth's gravity to pull us out of orbit when we want to return. That's how we get into space, how we stay there, and how we get back.
T-minus 10, 9, 8, 7, 6. We go for main engine start. We have main engine start.
Bye.